Right. Today we are going to learn how to perform simple linear regression using R. It's very easy, just like what you have learned in the regression course. You don't have to do anything manually, but you have to be conscious about the output. You should know how to read the output. You should be able to get the proper output. You have to check for assumptions, and you have to carefully interpret everything. So this is okay. I'll start off by giving a question. Anyway, the dataset is with you now. It is there in the LMS. So let me write the question for you so that y'all can copy it down. First, we have to know when to use a simple linear regression scenario, right? So let me write that for you. Okay, so this is the question, right? An engineer, you can even either write with me or you can take a screenshot at the end. An engineer at a medical device company wants to determine whether the company's new blood pressure monitor I'll just write BP for blood pressure, okay? BP monitor is equivalent to a similar monitor that is made by a different company. The engineer measures the systolic blood pressure. All right, he measures the systolic blood pressure of a random sample of 60 people. Using both monitors. So what is this experiment? An engineer produces a new BP machine, a new BP monitor to the company, and there's one existing monitor. The current machine is there, right? By a different company, right? So the sample size is 60. There are 60 volunteers or maybe patients who's going to check their blood pressure using both these. And what the researcher wants to find out is whether both monitors measure the same value, right? Right. So the experiment is to determine whether, right? To determine whether this happens. Okay, so this is the scope. So in the data set, if I show you the data set, we have two columns, right? That means two variables. So for the new machine and the current machine, the existing machine, the old one, right? And the description is new means in the data set, there are two columns called new and current. So the new means the systolic blood pressure measurements using new monitor, right? Current means, so it's a blood pressure measurement, the pressure that is measured from the new machine. It's going to be our first variable. The second variable is the systolic blood pressure measurement using the old machine or the current machine, right? So by looking at this, I'll show you the data set as well. I hope you'll have already downloaded it. But let me show you. This is the data set. So all these are blood pressure readings of the same individual, right? Two dependent samples, right? So they take the first patient, measure the blood pressure from the new machine, measure the blood pressure from the current machine. Take the second patient, measure it from the new machine, measure it from the current machine. So likewise, they have taken 60 people. The 61 is because we have column headings. So we have 60 people in the sample, and for every person, they have measured the blood pressure at the same time. We have to assume that they are under similar conditions because the blood pressure might change in minutes. So let's just assume from the new machine, they're taking it from the right hand, from the old machine, they're taking it from the left hand or something like that. At the same time, we have to assume that. So they are going to see whether the new machine is equivalent to the current machine so that they can replace, right? If there are errors, if there are problems, if the current machine did not show any problem, right? Just because it is old, they're going to replace a new one. They want the new one to act the same way just as the current machine. So how are we going to determine that? Two sample t-test? I said no. Why are we going for regression? Why not two sample t-test? It is incorrect to use two sample t-test in this case. Why? Can somebody answer? Just guess and tell me. To compare these two machines, whether they are going to be the same or not, we cannot use a t-test or any non-parametric statistical test. We cannot go for a mean comparison or anything. Why? Can someone respond? Just a guessed answer, that's fine. We are going to use simple linear regression here. So that is the hint. We are going to regress these two, right? One is a response, one is the predictor variable, and we are going to fit a model for that, but not t-test or any statistical test. Why? No guesses? It's easy. Like, yeah, please.
Madam, since we cannot calculate a critical value to compare with the p-value calculated by t-test.
Why cannot we compute a critical value? Why do you think like that? The data set is there. So actually, what is the data? Thank you for the answer, Imish. But the thing is, why? Just think it in this way. Why are we doing a t-test? To compare means, right? Mean reading from the new machine is equal to mean reading from the current machine, versus mean reading from the new machine is not equal to mean reading from the current machine. It can be any inequality as well. That is going to be our hypothesis, S0 and S1. Is that what we really need here? Because we have to see the one-to-one relationship We are not interested about checking any mean. Although the mean is the same, the readings might not be the same from the both machines. So they are going to replace the current machine from the new machine. So they really want each and every reading to be 1-to-1, right? If this is 100, they expect this to be 100. If this is 120, they expect this to be 120, right? So interchanging these two, just assume this is 120, right? And assume that these two are interchanged. Just take this block. Let's say you have 2 people in the sample, right? Just forget about these columns. You have 2 people in the sample, first person, second person, right? So if they really want to replace this one, it should give the same similar sort of a reading from the new one, right? What if we have something like this? I'll make this 120, right? And I make this one 120 and this one 100. If you compare the means, mean of this one is equal to mean of this one. Mean of this one is equal to mean of this one. That happens in both the cases, right? If we compare the means are equal. But when you get the first person's reading, person 1, when you get the first person's reading, the current machine gives 100, the new machine gives 120. So the machines are not acting the same way, right? That is why we need to incorporate 1-to-1 relationship here. And that is why performing a mean comparison test or median comparison test is not correct here. Is that clear?
Yes, ma'am.
Right, okay. Actually, we can find the critical value. The thing is, we have to see the distribution of this data. If it is normal, we can go for a t-test, right? So we know the degrees of freedom as long as we know the sample size. So Tn minus 2 is 58 degrees of freedom. So if we know the sample size and so the degrees of freedom, we can check the critical value if this follows a normal distribution. If not, we have to go for a proper non-parametric test. And there also, we can compare the critical value and get our test done. But the thing is, test is not suitable for this sort of a thing. So that should be made known. That is why when it comes to statistical computation, it's, just giving commands is not really the case here. We have to identify the situation. We have to carefully decide which method to be adapted given the situation, right? So be careful with that. At the exam, sometimes I might not say to fit a simple linear regression line, right? But the scenario is given for you all to identify it clearly, right? So you can be cautious about that. Right. Okay. So here, these are the description of this. And mean comparison is wrong because I want to match 1-to-1 rating. That is the answer for this, right? So I'll write that for you. So that we have to go for a simple linear regression. Why simple? Because we just have one predictor and one response. Okay, so here the next challenge is, okay, now we identified, given the question and the data set, we have to perform an SLR, simple linear regression. Now our next challenge is identifying X and Y. So just imagine the scenario. I know both these are measured in same scale. So according to the situation, what is X and what is Y? Any guesses? No, don't guess. Just read the question, understand. So Y is what? The response variable, the dependent variable. It is depending on the predictor variable. Predictor means the X variable. So by thinking like that, okay, I'll just give you another example. Assume that we are going to model human height versus human weight. There are also people can argue those are measured in the same scale of measurement, the ratio scale. It could be either the X or Y. No, because actually the height comes in the X-axis. Depending on the height, because Y is the response which is dependent on X. X is, we cannot control X, right? Here, we cannot control X. Height, you can't control the height, but you can control the weight. So when the height is changing, how the weight changes. So height is going to be our X-axis, the X predictor variable. In that case, weight is going to be our Y variable. So thinking in that way, what is X here? What is Y here? Anybody?
The current one is the independent variable.
Yes, exactly. Thank you. This is X and this is Y. Independent. Why we cannot control this? It is already there. Current means it's existing. New one is the one we are going to check whether it's equivalent or not. So how the new readings change with the current readings. So this is constant. This is also constant, but with this we are checking this, how this new reading is depending on the current one. Are they the same? Are they going to be the different? So giving that idea, when we are performing SLR, current machine should be our predictor variable, the independent variable. This is response. If there's any question, please ask, because they should be understood, as you all are doing the regression course as well. So yeah, so if the new readings is equal to the old machine, if we are getting a 45-degree line, right, some positive with a positive trend, that means these are changing in the same way, right? Okay. So first, when we are doing this, we can import the data set first. This is Excel. All right. Just to make the script complete, I'll copy these lines to the script. And if we view this is our data set. We have 60 members in the sample. So just to give it a start, we can start plotting this. Give me a second. Right, so how do we plot this? Just give plot, and always in this plot command, see the order we have to give the X variable first. So it's the current. So before that, we have to attach this. Otherwise, we have to call this by BP dollar current likewise. So it's time consuming. We can simply attach this so that you don't have to call it with the dollar sign. The name of the data frame, you don't have to use it, just the column name is fine. So attach BP. So you can simply use this. Just be careful about the cases. Right, it's capital C here. Those are the small cases that may come up with errors.
Excuse me, madam.
Yes.
Madam, we cannot see the R script.
Oh, sorry. Okay. Thank you for that. So first I imported the data set and we did, and then attached it so that I can call it by the variable name. Otherwise I have to go like BP dollar current, BP dollar new likewise. So that is time consuming, that is very tedious. So I did this way. So when we plot this, it seems to have this type of a shape, but we have to set a model and see whether it is significant, things like that. So our main focus here is to learn how to perform a simple linear regression. So once we plot that, if we want to measure the correlation, for example, Pearson's correlation, so the command is this, correlation of current and new. There actually the order is not important. So correlation is what? It's highly correlated. Right? Although it is given this way, sometimes by looking at the plot, you can see this is okay. Even if you do a hypothesis test for correlation, it will say that this has some correlation, right? So by looking at this, we really can say, but that's why we plot this before, right? Just assume that you have some data points here, like in a circle, and you have just one data point here. Still, it is going to give you a strong correlation because they're checking it along this way, right? This one here, we have a patch here. Just assume we have just one dot. Still, it will give you this correlation, but it is wrong. And this should be outliers in that case. So that is why it is important to do a test. So the correlation test is cur.test, right? So we can have the same names. So when we did, so this is Pearson's product movement correlation test, right? This is the correlation test, and here this is the estimate which we got earlier, and here we have to check the p-value. It's very small, even R cannot write it, so that's why it says p-value is less than this value. This is 0.16 zeros to 14 zeros to 2, right? So it's a very small p-value, which means it is highly correlated. How did I exactly say that? In the correlation test, what is H0? These things we have discussed, although it is not the correlation test we have. So H0 is H0 is always null. There's no correlation. Versus H1 is there is correlation. So we reject, decision rule is what? We reject H0 if p-value is less than our significant level, 5%. So this is less than the small value, the smallest value that we can see here. So anyway, it should be less than 0.05 if that is the case. So this is very small. So we reject H0. We reject we reject H naught means, did I reconnect? Did you hear what I said? I think this.
Yes, ma'am.
Okay. So here, by looking at this p-value, we can definitely reject this H naught according to the common decision rule that we use. So we can say it is highly correlated, right? Just by looking at the plot, just by looking at this value, we cannot say. We have to do a hypothesis test. Right. Now we can do a regression analysis. So let me tell you how to fit a linear model, simple linear model, that is LM, right? LM for linear model. And here we have to give the y variable first, right? New, and then put a space and type this tilde mark. In my keyboard, it is in the left corner underneath the escape button, escape key in my keyboard. So you should be able to find it, the tilde mark, okay? New tilde, then you have to give your predictor variable. So that is basically this, right? You can either run this as it is, or you can just assign it to an object, right? Let's say BP model. It's very clear when you write it like that. So you can reuse this easily. So you run that, now you have fitted it. Let's see how it looks. Here, this is the intercept. Here, this is actually the model is what? Beta naught plus beta 1 current, right? New is equal to new hat, okay? Estimated one, new hat is equal to beta naught hat, this is the intercept, plus beta 1 hat times the predictor variable current. Okay, so here this is beta naught, which is under intercept. This is the coefficient of this predictor variable current. Basically, this is beta 1 hat, right? So this is the output. So if you get this, and if I ask you to write a model, write the model, you can simply write mu is equal to 1.3867 plus 0.9894 current. That's how you have to write. Run the R code and write the regression model. You have to write it like that. Okay. And we can see the summary. This is easy if we assign it to an object like this so that we can call it in this. Otherwise, we have to run this line here. Okay. So in this summary, they give a lot of information. So by this, you can identify you have fitted a simple linear model, regression model. So these are the descriptive statistics of the residuals, right? And the coefficients, the same thing. This is actually an ANOVA table if you look closer, but the error is not there, the total is not there, right? The estimated value is there, right? No, sorry, this is not the ANOVA table. But it looks like the ANOVA table, right? The t-value is there, standard error is there. So these are about the coefficients, right? To get the ANOVA table, we have another command. It looks something very similar. So residual standard error, 58 degrees of freedom, right? Multiple R, this is the R squared value. I'll teach you about adjusted R squared when we discuss the multiple linear regression in the regression course, right? So here, just because this is simple linear regression, we have to consider this R squared, F statistics and all that. So here the p-value is less than this one, so we reject H naught, right? So actually what is H naught here? In this case, model is not significant. Beta 1 is equal to 0. Right? So we'll see, but just by looking at this one, we cannot say anything. We have to check for model assumptions. Before that, let's go for the ANOVA. If we want to get the ANOVA table, this is analysis of variance, ANOVA. So here actually, they have interchanged the way that we are used to do, right? We usually go in the source of variation, sums of squares, degrees of freedom, mean square, F value, right? So here they give the degrees of freedom first and then the sums of squares. So this is the sums of squares of this one. This is the sums of squares of residual, the error. The total sums of squares is not given because it's obvious, right? You can simply add these two and get the SSTO, right? Total sums of squares. Degrees of freedom is this. So this is n minus 2. We have just one predictor variable. So this degrees of freedom is 1. Likewise, mean square, this divided by this is given here. This divided by this is given here, and the F value. So they have additionally, just because this is software, they give the this thing as well. So according to this one, they give star 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 means this is significant, right? Even without looking at this, if you see the stars, you can see this variable is significant, right? But just being significant is not enough, right? We know, okay, a model exists. There is a highly correlated relationship between these two. But in order to use this particular line, so what is the line that we got? 1.38669 plus 0.98936 times current. So when we give values to current, by using this particular formula, they're going to estimate the new value, right? So although the model is significant, we have to go and check for model assumptions. What are the assumptions to do a regression? There's a couple of assumptions that you have to check, right? You have to see whether the errors are independent, the errors follow a normal distribution. Likewise, there's quite a lot of things that you have to consider. If at least one of them gets violated, you have to do something and get the residuals, get the model meet the assumptions. Okay, so let me so we can simply use the Shapiro test for normality of residuals, but I just want to introduce another normality test which we highly use in regression, that is Anderson-Darling test. So that is actually not in the base package. We have to install it from NOR test package. So you have to have an internet connection to this. NOR tests, this one. Install dependencies and then install. We install this. It takes a bit of time to get installed. Right, so now it's done. Then we have to call the library. Now the package is activated. Now we can simply do the Anderson-Darling test. Okay, so the command is ad.test. Here we, what do we check here? Normality of residuals, right? So how do we access the residuals of this model? That is the next important thing. BP model is the model that we already fitted, right? So yeah, just consider this ANOVA, right? ANOVA of BP model. So in this BP model, you can access these things, right? So you can, if you want to print the residuals of this particular model, then you can simply get it by using the dollar sign, BP model dollar residuals likewise. So we'll do that thing first. So here, can you see? If you want to get the fitted values, this is the way, right? If you want to get the rank, effects, coefficients, right? If you want to get the intercept and the slope parameter by using the word coefficients, you can get it, right? So here I want to show residuals, right? When you these are the residuals of all the 60 observations, right? We can even plot this and see, right? So we'll perform the Anderson-Darling test for residuals. So we have extracted it. So it is the normal test here. H naught is here. The p-value is this one. So this is actually less than 0.05. So we rejected slot. Now what has happened? The model assumptions have not met. If this is met, no problem. You can stop from here. Either you can just plot the residuals versus fitted values and see, right? But here actually the errors are not normally distributed. So without even checking anything else, we have to do something, some adjustments for this and refit our regression model, right? If these are normally distributed, then you can check the other model assumptions, independency of errors and all that, variance and constant variance and all that. And if everything is met, you can use the fitted model for future prediction. But here actually, by just because this thing violated, this is less than 0.05, right? So we cannot use this model, right? If you want, you can plot and see. You can either plot the BP model. When you say plot BP model, actually it gives us 4 plots. So we are going to partition this pane into 4. Two times 2. All the plots are coming. Otherwise, you have to press and keep on pressing enter 4 times. You are getting individual plots. So when I zoom it, can you see residuals versus fitted values? Yes, it's going in a constant way, but where in 0, right? This line is aligned to 0. So this is okay. Normality plot, actually these things should go along this line, not exactly, but approximately it should. But you can see some deviation along these two, right? So actually this leverage is to find the outliers. We are not interested in that. So here standardized residuals versus fitted values. So it also shows us the constant band. So actually we can see the errors are independent and the mean of errors is 0. But the problem is when we do the Anderson-Darling test, or you can either do Shapiro test, right? Errors are not normally distributed. So somebody can say something like this: the sample size is 60, which is greater than 30. So we can assume it to be the large sample case, so that we are going to assume normality and proceed. That is just one way. So if that is the way, we are going to end the lecture now, right? So I'm going to teach you something additional, some additional thing in real life. If this happens, how are we going to handle the situation? Anyway, we cannot stop from here. Just because it does not meet the model assumptions, we cannot say okay, we don't have a regression here. We cannot do any regression between these two. So we are going to stop the process. You can't do that. You anyway have to come up with some particular model. So the first thing that people try to do is transforming the variables. So just because I want to teach you something additionally, without assuming the error, the residual normality, although all the other assumptions are met, I'm going to transform the variable and going to fit a new regression model. Just for your knowledge, right? Actually, in practice, that is how we do, right? So let's do that. Right? Usually, what people start doing by is getting the log transformation of the response variable. Okay, so I'll denote it as L mu, right? Oh, just log mu. So this is going to be our response variable. We don't know whether this transformation would work or not, right? If this didn't work, then we have to go for some other transformations. So you can read from literature, you can take similar research and find how people have done it, right? But usually this is sort of a trial and error method. These are not hard and fast rules. Some people just go along with this model without doing anything, right? So here we can see really whether the log transformation helps us in getting the normality of residuals. So the command is, okay, right? So here now we are going to fit the regression model. So a new model, or I'll say regression VP model 2, the second model that I'm going to fit, right? Linear model. So I'm going to fit the linear model between the log transformed y variable with our x variable. If this is not understood, just ask me. Okay. Just because the errors are not normal, I'm going to do some transformation and see whether this is what. Right? So when we run it, this is the intercept, this is the slope parameter. So according to, sorry, this was wrong. This is the intercept and this is our slope parameters. Can you see this was the old one? This is the new one. Okay, this is the new regression model that we fitted. Here also we can do ANOVA and all that. Right, here also, even this model is significant. The p-value is very small, right? When we get the ANOVA. So even this model is significant. The model between the current values and the log of new values. Right, you can either check the correlation. You can do, so when we are getting the correlation, it should be this one. See, correlation is again very high, right? Same thing you can do. So before doing anything, why did we do the transformation? We think that the residuals will become normally distributed when it comes to the log scale of the response variable. That is what we thought, right? It doesn't happen all the time, but most of the time, yes. So that is why we tried starting from this. We started trying here, right? So before doing any of these, you can actually check for the normality of residuals. So once you fitted the ANOVA, I'll say residuals 2, right? The new model's residuals. So how are you going to get that? BP model $2 the residuals. right? Then you can print and see. These are the new residuals, right? So you can do these things, Anderson-Darling test, right? And plot it. So AD.test. You can either do the Shapiro test, doesn't matter. But usually we do this one with regression. There's no particular reason for that. Okay, now the p-value is again less than 0.05, but it is very closer to 0.05. So actually, it doesn't have to be 5% all the time. You can even change the significance level, right? So if this is, if we consider 0.05, again, the normality assumption gets violated, right? What if you get 0.01? Then p-value is greater than your alpha, and you can say it's according to 1% significance level, the data are normally distributed. So just because we don't want to keep on trialing and errors, I'll conclude that this follows a normal distribution, defining the decision rule with 1% significant level, right? So here, if you don't like it, you can do further transformation and see, right? So what is the next transformation? I don't know. We have to trial error and get it, right? Usually what people do is this one. So here the p-value is this. Right. So let me write the decision rule, otherwise you might forget this. I'm interested in 1% significance level now. I cannot handle 5%. So reject S naught if p-value is less than. Okay. So what is the decision here? Actually, p-value is greater than this, so data are normally distributed. You can simply say residuals are normally distributed. So at the exam, don't worry. You are given this particular significance level, you don't have to think whether you are going to use 5% or 1% or anything. Everything is given to you, right, at the exam. So don't worry, everything will be given clearly. Evidence to reject with, is it correct to write 5% here? No, 1% level of significance. This is the real challenge when it comes to real world data. Okay. Now you all know how to do transformations, fitting the line and all that. They're going to be the same, and we can check the other model assumptions as well. Plot VT model 2. So this was the earlier one. This is the new one. So when you check this again, the residuals, they are going in the same way. Now still this shows up some tailing off here, but better than the previous one, right? Little better than the previous one. So according to 5% significance level, it's not normal, but for 1% significant level, it is normal. So you can either get this one, or if you like, you can go to the first model. Like in regression, it is subjective, right? Person to person, it has a possibility to change depending on how you decide. At the exam, it's not going to be a problem for you, but in real world, people can make assumptions and use whatever the model they got, right? For the same data set, there could be a couple of models in practical scenario. There could be a couple of models. So for different criteria, we can find the best model, right? When it comes to time series, we check for AIZ, BIZ values. We archaic information criteria, that one. So when it comes to this one, we can split our data set into the test set and the training set, and then try to predict by using it, right? By using the test set, whether we can see whether we are getting the similar numbers. So there are a couple of ways of checking the best model. So that comes in practical situation. So don't misunderstand. When the data set is constant, it's not really the same model that you're going to end up. Doesn't have to, right? You can come up with better models. You can improve models all the time. That is why the research industry is never ending, because one can find some model, the future researchers can improve it. What do you mean by improving? They're doing transformation, they're adding some variables, maybe they're deleting variables, they're fitting different types of model. It doesn't have to be linear all the time, it could be even non-linear, right? So some people make a lot of assumptions, like in the earlier case, what if we make use of the previous model, this one? There we assume that the errors are normally distributed just by looking at the QQ plot. It seems like it goes in a line, although it is tailing off here. But just because it meets the other assumptions, somebody can say, okay, we are going to disregard that. The sample size is large, considerably large, so we can assume normality and use this model. Somebody can make transformations and go to a new model when predicting, right? So that is not static. When it comes to the exam, it's static, right? But in practice, it doesn't have to be, right? So you learned that one as well. Okay, so we plotted, and according to 1% significance level, we can say this is normal distributed, and other plots are all okay. This is seeming the standard residuals, and this one is going in a constant band, so variance is constant, and it's the mean is 0, right? This is the 0 line. So mean of the residuals are 0. Right. So I decided to use this model as my final model without doing further transformations. So we can go ahead. If we want to access the coefficients, right, without copy pasting from the ANOVA, we'll do the ANOVA for this. We did it right. The new model. So rather than the summary. Summary. So rather than copying and pasting the estimated values, so now what is the model? Log of nu is equal to 3.8057184 plus 0.0081 current. Okay, that is the new model. Don't write nu is equal to this one plus this one times current. Now we have transformed the model, right? So now the model is log of nu is equal to this one plus this one times current, right? So if you want to access these things, it's very easy. You can, there are a couple of ways, right? Coef of BP model $2. So one within, so not dollar, within square brackets, if you give 1, it is going to access this value, the first value, that is the interceptor. This one is here, intercept. If you want to access it, so these are features of R. right? So if you want to access the slope parameter, that is this one. I'll just write beta naught here for your future reference. It's the second one. Likewise, you can access coefficients. If you want to construct confidence intervals, it's very easy, just a matter of giving one line, content, content. You are going to get the confidence interval for the parameters for beta 1 and beta naught both. They are giving confidence interval for both. You can give the level of significance if you would like to. Otherwise, by default, they would carry on 95% confidence level. BP model. Can give the level of significance like this. So you can either give 0.99 just because we are in that one. 99% confidence means 1% significance. So just because we, to make it consistent, I'm going to have it like this. There's no problem. You can even get 90% confidence intervals. That's fine, right? It doesn't have to be the same all the time. What is important is when you are reporting, you have to report the significance level that you consider. Just because this is 1%, it doesn't have to be 99%. You can have 80% even, doesn't matter, right? I just, to make it consistent, I just put this value. So this is the lower limit. This is the upper limit of beta naught. This is the way that they are giving the confidence interval, right? Here, this is the lower limit. This is the upper limit of the slope parameter, that is beta 1 confidence interval to this percent. If you want to get 95% confidence interval, it's different. It gives you slightly different values, right? So this is the 2.5th percentile. This is the 97.5th percentile because it's 95% confidence. Here, this is this one. Anyway, this is the lower limit. This is the upper limit, right? Even if you want to, you can have 90% confidence. So this is 5%. This is the gap between these two is 90. The gap between these two is 95. The gap between these two is 99. Likewise, 5th percentile, 95th percentile. So this is the lower limit. This is the upper limit of beta naught. So when you get this, right, in the paper, if you're asked to get a confidence interval for beta 1, don't write all these because you have to convey me that you know how to read this output, right? Otherwise, you're going to lose marks. If I say slope parameter, don't give me both these because I can't choose. I don't know whether you know it, right? So if it is slope parameter, only give this one. Put a square bracket and write it. Write what you got in the script, right? So you should be very careful in reading. You should know how to read the output. So this is the confidence interval for beta naught. This is the confidence interval for beta 1. If I ask both, write both, right? So when answering questions, don't overwrite, right? Overwrite means not writing on top. Don't write lengthy things. Just be to the point. Okay, so we can take the variance covariance matrix and see. You will be familiar with this once we do the multiple linear regression. We just discussed about that in the regression class slightly. So when you're getting, this is a matrix, right? So intercept, these are the variance terms. And can you see this is going to be repeated here, same value, right? The diagonal terms, variance of intercept, variance of current, the variance of the slope, right? This is the variance of the intercept, this is the variance of the slope. Here, it's the variance between these, right? So like that, you can do many things. and assume that you are going to predict by using this model. Predicting means what? You are giving a new value to the model. Now, let's write the model first. Log new is equal to this one plus. Actually, this is hat. I'm not writing hat here, but you all know it, right? It's very confusing to write many different things. This is hat. Just put a hat there. Okay, this is our model. Predicting ability means that when you give values to this one, right, given the value of current, how the log new is changing, right? So when you keep on substituting values to these one, you are getting corresponding values of this one. And you have to get the back transformation, right? This is the log new, but we are interested about new. So you get the log value and you get the exponential, right? This log means ln to the base e. In R, log means not to the base 10, right? Log means to the base e exponential, right? So remember that log transformation in R, log gives you the log e transformation, not log 10. Okay, unlike the basic mathematics that we do. So this is our model. Here, if we want to predict values to all the current values that we have here, right? So assume this one, we are going to get the log new value by using this model. It doesn't have to be this one, although you get the back transformation, because these are true values. Now we are going to get the fitted values, right? We can see how well this model is fit. So if you want, in general, if you want to get the value, the predicted value for the existing current values, that means all the current values in the data set itself, this is the way, right? Let's say y hat, right? The command is predict. You give the name of the model that you fitted. So we are using this model. And this command. It's better to do it this way. Okay, so actually this current means this current. This current means the set of values that we are going to substitute in this. It can be even a single number, or it can be a vector of values, right? Here what we give is to the existing values, to all these 60 values. Here we are going to get the fitted value, right? So this current means the variable current. This means the values that we are going to give. Okay, so when we type y hat, you should be getting 60 values. See, you're getting 60 values. These are the predicted log new hat values, right? So to obtain the new values means predicted these values, you have to get the back transformation just because you had the log transformation in here. If you use BP model rather than using BP model 2, you don't have to do any back transformation. You can simply get this, right? But here, can you see these are all 4-point values, but what we expect is to get 100, 120 likewise. So how do we do the back transformation if it is log? That is exp. I see we are getting, now these are the new values according to the model that we fitted, right? When we keep on substituting values to this one, what are the values? 100, 120, 132, 139 likewise. We are getting new values as these for all the 60. Assume that you want to predict just one value. How are you going to give? So I'll write by pred, just a name. So current, I want to see if the current reading is 50, but no, don't write 50. Let me tell you one more thing. Minimum of current. Right, so the minimum value of current is this. You might be wondering why I'm doing this. I'll explain. Maximum of current. That is 146. Right? In regression, the extrapolation is not advised. What do you mean by extrapolation? Assume that you got this, right? So this value is what? 97. This value is what? 146, right? You fitted whatever the model to this particular data set within this scope. We don't know the values which comes before 97 and after 146 behave the same way. When this line is fitted, we don't know whether this is declining or going in the same way or this is going in a curved shape. We don't know, right? Usually it should give the same thing, but we fitted the regression model to the scope. So if somebody asks you to get the log new, the new value when the current value, the BP reading, blood pressure reading is 70, yes, you can type 70 here and get the log new value and get the back transformed value, right? But you cannot guarantee that it is whether the accuracy of the value that you got, because it is not in this range. If somebody asks you, okay, the current value, the existing machine gives you the reading 200, what will the value of the new machine be, right? You can put 200 here, get the value. Just because we are getting the log value, you can get the exponential and get the new reading, but you cannot guarantee why, because it's not within the region. 200 is not within the region, right? So whenever you have to do predictions, it's always advised to stay within the scope, because extrapolation is not advised in the regression model, any regression model. You could be asked that. Predict some outer value will be given to you, and what can you say about the value that you obtained? You have to say you cannot guarantee about the value because it is not within the scope. You have to extrapolate the line to get it, right? It is true, no? These are going to negative infinity and positive infinity, right? If you give -1 as the current value, you are getting some new value, right? So if you give -1 or something like that, so the pressure cannot be -1 anyway, right? Pressure terms fluctuates from 50 and 300, let's say, usual in practical scenario, the pressure values. But even if you give -1 here, you are getting an answer, which is not meaningful, right? So even by looking at the context, you can say that, but the general answer is extrapolation is not advised here. So you cannot guarantee the predicted value beyond the scope, right? So if you want, so these are the values that you have. So you don't have a value, do you have any? 145 is not there. Okay, let's say you want to predict some value. When the current value is 140, it is within the scope, so we can predict it, right? Right, so y-pred is what? Log of the value, okay? Now, remember that. You did I run this? Predict this one. Why is it giving this way? You have to give it as a list. This is the command. Let me just. Okay. You have to give it as a list. So if you want to get the new value, when the current value is 140, yes, you can guarantee this, it's within the scope, right? So when you ask to interpret, you can say when the current value is 140, the new machine will give you not this, right? You have to get the exponential. See, when it is 140, the new value is 140 point this. So it's going very close. So you can give different values within the scope and answer the question saying that the new machine is going to perform the same way as the current machine because it gives similar values, right? It gives you 45-degree line. You can plot this and see whether it's 45-degree, but you can take the intercept, right, and see the slope, right, and see whether it is 45-degree, the tan value, and see whether it is 45. If this is 45, then that means the current one and the new one is going to be, this is the old graph. We'll just plot the why do we no we don't have to plot with the log one, but still it should give the 45-degree line. Let's see. X value is current. If you want a single plot, so let's go. It's giving that 45-degree line because log scale is just shrinking the scale, right? Getting log is just shrinking. These hundreds are shrink to 4, 5, that range. So this is not meaningful, like no need to do this. So whenever you are asked to predict something, you have to get the model. You have to check for model assumptions, and if they are not violating, you can simply use the model. If they are violating, you have to do transformations and again fit the model and then do the same thing. You have to repeat the same process until all the assumptions are met, and take whatever the final model with whatever the transformations that you have, right? Sometimes you will have to do transformation for the x variable. Sometimes when it is non-linear, most probably we square this and see, right? There are so many trial and error techniques. So this is the most general one, taking the log transformation of the the response variable, and it worked in our case for one present significance level. All the assumptions are met, so no problem. We end up fitting this model, right? We are happy with this model, so we are going to use it in predicting. So if we want to predict another set of values, let's say, I'll just delete this, this is not necessary. Let's say you want to have different values. 130, 99. Yeah, you can keep this like this. So when the current value is 140, log new value is this one. When the current value is 130, log new value is this one. When it is 99, log new value is this one. but we are not interested in log new value. That is our model. We want to get the new value, right? So you have to get the back transformation exponential. So when this is 140, this is going to be this one. 130 is very close to 130. So by looking at these, you can say, when you get the tan value, right? This one minus this one divided by this one minus this one, right? So you can get the slope and see. Anyway, the slope is there. Slope is close to 1, I think. Okay, not in this. Right. So we learned to fit a correct regression model, which which we can get all the predictions. So this is the complete regression analysis, simple linear regression analysis that we can do. And to answer the question, actually, we don't have to check model assumptions or anything, because our question, what does our question ask? Whether this relationship is 1-to-1. That is what our question asks, right? What is our question? We want to see whether this is equal to this one, right? So just by getting the initial model, I forgot to show that to you. We first have to answer the question and then keep on doing the regression. So here, what is the intercept? Intercept is this one. So we are checking whether the current value and the new value are 1-to-1. That means the slope should be 1. So can you see the slope is 0.989, means approximately it's 1, right? The slope parameter value is approximately 1. That means to answer the question that I gave you, you just can fit the model and look at the slope parameter. That is all what you have to do. So I asked you whether the new machine or old machine, the current machine could be replaced by the new machine. How to answer that? Fit a linear model, put the summary, get the summary, and get the value of the slope parameter. If it is 1, we are done. We can say the relationship between these two is 1-to-1, right? Because this is 1 means what? Tan 45, right? It's 1, right? Tan 45 is 1. So this is 1. You can say this is very close to 1, which means this shows a 1-to-1 relationship. So you can replace the current machine by the new machine. So that is done. Why do we go further? Just because we fitted a regression line, we can make use of that to do predictions and all that. Now we are done deciding whether the current machine could be replaced by the new machine. We are done with that, right? Here, what we do is, in order to proceed, if you want to further fit a model and do predictions within the scope without extrapolating, then we have to check the model assumptions. And if it is not working, we have to do transformations and all that, right? Anyway, the log transformation would never give you 1, right? It is shrink. This is 100, 110, 120. Likewise, this is 4.6, 4.7. So this is not 1-to-1, right? This is a shrinked axis. So you have to check whether it is 1-to-1 or not by without doing any transformation, right? So the command is actually simple linear regression in R. That is the command that we have to do to answer that question. But thereafter, you can further proceed to come up with a correct, acceptable, usable model. So that is why we did. We checked all the assumptions and all that. We found out that the assumptions are not met. So we did a transformation, and there we found out the assumptions were met. No problem. We use that model to predict values. You can use this command. The list should be there. either one value or either all the values that you used in the data set, you can do predictions. Right. What else? Then getting the confidence band. So yeah, I think we discussed that in the regression lecture as well. This is the last one for today. So here we are going to plot the current and the new model, and we are going to get the regression band, right? So plot. Our model is what? Log new. Log new. First we have to give the X variable. You can either give log new, but when you give log new, just because the axis is shrinked, you cannot see the band properly. It's not incorrect. You can either give this way or just this one, right? Because this is what we are interested about. To do predictions, we have to use this model. To plot and show you the confidence band, you can simply use this one, right? I'll do both ways. All are correct. We have to plot this line first and then give this command map lines, right? You have to give current and I want the confidence band along all these, so I have to consider everything. Where is that? That is y hat, right? Y hat is the object that we saved, which gives the predicted values for all the current values. Yeah, that is the case. We have to, yeah, we'll see this way. It should be log new because these y hat values are gotten from this. We'll see. Both ways should be correct. Then you have to, you can give colors. So when you're giving colors as a command, it's a vector. So the first, so in the confidence band, right? The confidence interval for each and every observation, that is what you call by confidence band. Upper limits are joined by this line, lower limits are joined by this line, and the regression lines goes in between. But when you are giving the colors, you first give the color of the regression line, right? Let's say black, right? And then you have to give the colors of the two confidence band. So usually you give the same color. Let's say blue. If you want, you can give 3 different colors, doesn't matter. We have to, I don't know whether this will. Okay, we have to create the confidence interval first. Forgot that, sorry. So copy this command. Right, same command here. Actually, we have to get the confidence interval. How we get that? Int equals, within brackets, we within inverted commas, we give C for confidence. If we want a prediction interval, we have to give P, right? So here we are interested in getting a confidence interval. So what did we get here? Y hat conf. Right. What did we get here? All the fitted values by using this model for this one, right? Here we are getting confidence values, and you can give the level of significance as well, level of confidence as well. Level equals 0.99 or whatever, 95 or anything. This should be given here. So just because this is the log scale, it is very hard to see the gaps between the bands. So for the data set, this line is, the black line is the regression line, the blue lines are the confidence lines. I'll make this red. Now it's clear. This red line is the regression line. These two blue lines give you the confidence band, right? So to get the confidence band, you have to specify the interval, right? Otherwise, the predicted values, it's going to be the same thing. It's drawing on top of the black line. So for confidence values, you have to get it like this and then plot these and get the MAC lines. I think this should work for the new one as well. Let me check that. No, not getting, because this is in the 100 scale. Same thing, you have to get the exponential here. This is 100, so it's not going to work. Right, so if you fit the model to be this one, you have to get the confidence interval at a given level by using this particular model, this one, and then you can plot it between the new x and y variable. So x is x, y variable is log of the transformed variable, and the MAC line is the command that you give to draw lines. So when you plot this, you are getting the plot, right? When you run this particular line only, on top of this plot, you are getting the values. If you notice, see, you are getting the values on top. Right. Okay. Anyway, yes, this is 4 point something. You can't give new value here. Right. So that is all for today. We can discuss a little bit about multiple linear regression next time. So today's scope was answering the first question, that is why for this kind of a situation, why a mean comparison is wrong, why we go for a regression model. Our intention was to see whether this has a one-to-one relationship. So when we fit a regression, the slope parameter should be 1, right? If it has a one-to-one relationship, it should give y equals mx like line, right? The intercept parameter should be 0. If it has a one-to-one relationship, it's not exactly 0, but you know, it should be very closer to 0. We'll run that and see. Summary of BP model. See, summary of BP model. Yeah. So intercept is 1 point something. It should be 0. Does it? No, it doesn't have to be 0. but very close to 0, because we expect the same reading actually, right? If this is 100, we don't want the new one to read like 200. If this is 110, you don't want 2 times that thing, right? So we anyway check whether this slope is 1, because we need a 45-degree line. So if we get that, by commenting on this, you can answer the question, yes, it has a 1-to-1 relationship. So the current machine could be replaced by the new machine. Thereafter, we learned how to perform a general simple linear regression. So we just proceeded after that. We used the fitted model to check the assumptions first. Before predicting anything, you have to check for assumptions. And we found out that the assumptions were not met. They were not met. So we have to do a transformation in a way that the assumptions are met. So we found out the log transformation really worked. So we carried on getting the new model for predictions, right? We used that model. It is a valid model because it met all the assumptions. And we checked the ANOVA and we found out that the model is significant at the first place. Then we checked the assumptions. Then after checking the assumptions, as long as everything is correct, we went for predictions. We give different values for the current reading and checked the corresponding log values. Just because we had the transformation, remember we have to do the back transformation to get the actual reading, because we are not interested about log of new value, we are interested about the new value. So back transformation of ln is exponential. That is what we did here. And we recalled that extrapolation is not advised in regression. So whenever we are substituting values to this one, we have to be mindful that it should go in this range. It is not incorrect to go out of the range. The thing is, we cannot say whether it is correct or incorrect. It is not guaranteed. So at the exam, if I ask you to substitute some value and comment on that, just please check these things and see whether you have to extrapolate your line to get the predicted value. If that is the case, the comment should be what? We have gotten this value, but it cannot be guaranteed because this is extrapolation, right? So that is the answer you have to say. If I give a value between these two and try to ask you to give your comment, you can get the value and say when the current value takes this value, the new value takes that value. That is how you have to answer. When predicting, you can even predict everything here. Or if you want to predict some new value within the range, you can give this way. And if you want to simultaneously predict different values, you can give it as a vector within the list. That is how you do. So if you're asked to plot a confidence band, how you should do is first you have to fit for the interval. You have to give this interval command with this line, and then plot the fitted axis. And by using this command, you can plot the regression line. This color is given to the regression line. These colors are given to the confidence line, confidence band actually. So that was the order. Any questions from today's lecture? This is all. Any questions? Is this clear for you all? Any confusions? Let me know if there's any.
It's clear.
It's clear. Okay. I hope it's the same with the rest of the people as well. If not, just ask me at any time. You can practice this. So the data set is given. I'll upload this R script so that you can don't copy and paste, right? Just try to come up with your own commands. Just remember small things, right? These ones. So yeah, that is the end of today's lecture. Thank you very much for participating. Just because you don't have any questions, we can stop the meeting. Thank you very much.